Hello everyone, welcome again in Eng-Man YouTube channel. So in this video, we will have a case of electrical submersible pump design. Okay, so we will have a practical case right now. Hopefully we can learn something good in this particular video. Okay, so let's start. Yeah, I already have a template file. I'm going to use this, but yeah, hopefully if there's nothing problem, if there's no problem ahead, yeah, I will explain each of the step. Okay, hopefully we can cover that in a good period of time. All right, so the well, it's Eng-Man slash or Eng-Man dash X. This is the name of the well. It's imaginary well, of course. Location YouTube, something like that. Formation Eng-Man. Okay, and the perforation. Now my perforation is located at 3300 war 13 to 3353. Okay, so KB is Kelly Bushing, BH is Bradenhead, or it's like wellhead location. So the distance from Kelly Bushing to the wellhead is around 19.83 foot. Okay, so feet based on Bradenhead measured depth, it will be this one. Okay, and then this one minus this one. So middle of perforation will be the average of this and this. Okay, 3333. And I will set my ESP, the pump setting depth, or maybe I will use this one minus this one. Okay, 3317 fit this one. I sometimes like Bradenhead measured that because it's actually the reference point is the wellhead. Wellhead location will be the zero depth. So I usually prefer BHMD, okay, or wellhead measured depth. And in in this depth, I will locate my ESP at this one, at this location, 3250. So the KBMD is this plus this one, 3,266. Okay, so we will have this. Okay, okay, I have this formula. So if the ESP is below the middle of perforation, I will have OK note there. If not, PSD above mid perf, which is not good. Okay. Okay. Pump setting depth above mid perf. Okay. Yeah, usually you want to set your pump setting depth above the mid perf, right? But in some cases, actually want to set your pump below the mid perf if you have shroud, if you have shroud to protect, yeah, to to give you a high velocity so that you can cool down your motor. But in typical case, you prefer pump setting depth above the mid perf, so you will have cooling effect from the flow, the motor will be cooled, and the operation can be safe. Okay, but of course, if you have pump above mid perf, you need to take into account the potential of uh, gas lock, gas interference. So you need to have separator, gas separator. Okay. Uh, if you don't want to have gas problem, literature recommend you to put your pump setting depth below the perforation. But of course, if you have sand problem, it will be dangerous. Sand will go down and it will block your ESP. Okay, so yeah, I think in general cases you need to put your ESP, the pump setting depth, above mid perf. Okay. All right. So now let's enter into the inflow performance section. Liquid rate. I'm going to use this as target. So my target flow rate is 3,000 barrel liquid per day, and reservoir pressure based on static bottom hole pressure survey, it's 800 psig. Flowing bottom hole pressure FB HP, I don't know. Okay, let's say I don't know because this is a new well. I just work over my well, so I don't know. I don't have flow right now. I need to forecast I need to estimate my flowing bottom hole pressure if it is, if it can flow. Okay, but currently I don't know. So I will not use this value. Okay, I will skip it for now. Yeah, I can also delete it. Okay, and water cut, I know it's a water source well, so water cut will be 100% or 1 in fraction. Okay, and maximum flow rate, Qmax or absolute open flow. I know this one. Okay, I know this one because I already create analytical IPR using permeability, thickness, skin factor, right? I already know that. I already done that in well flow model. So the value is actually 5,457. Okay, 5,457. But in this sheet, this value is calculated using liquid flow rate, static bottom hole pressure, and flowing bottom hole pressure. So I'm going to use what if analysis. Okay, what if analysis, click on data, or maybe I just need to input a guess value first. So if I have flowing bottom hole pressure of 200, it will give me maximum flow rate of this one. Okay, but the correct value for my maximum flow rate based on well modeling, which I did, which I created in another software, it's 5,457. Okay, yeah, just a bit a bit note right now, a short note. So in well modeling software, okay, I created an analytical IPR, a theoretical IPR. I use permeability, thickness, I generate the IPR, the analytical IPR, and it gives me the productivity index value and the maximum flow rate value. Okay, and the maximum flow rate value, without knowing the flowing bottom hole pressure, it's 5,457. Okay, so I will instead calculate the flowing bottom hole pressure so that I get this value. Click on OK. All right. All right. So I can have maximum flow rate of 5,457 if I flow my well at this flow rate, at this static bottom hole pressure, and at this flowing bottom hole pressure. Okay. So the correct flowing bottom hole pressure, if this IPR is true, is 508. Okay, 508 psig. Okay, I hope you get the explanation there. And productivity index in this particular spreadsheet, I already use a quick look, you know, a quick look approach to calculate productivity index. It's very simple. We just need maximum flow rate and static bottom hole pressure. So it's 1.8 multiplied by Qmax divided by, divided by this static bottom hole pressure. Okay. It's a quick look approach to estimate productivity. Okay, but if you want to get a better calculation, a more accurate calculation from for productivity index, I recommend you to open the textbook. Okay. Okay, so liquid rate target, again, 3,000 barrel liquid per day. Yeah, this sheet, okay, this spreadsheet is developed in the assumption that you already have well test value. That's why initially it is written test. Okay, so you already have well tests and then you want to change or you want to optimize your your ESP, you can use this spreadsheet. Okay, but in this case, I don't have well test data. I don't have well test data because it's a new well. I never flow my well. Okay, so that's why I will, yeah, so that's why I need to use some adaptation, okay, to use this spreadsheet in the case of new well. Okay, so yeah, let's say in imagination we have already the well test data 3000, which is the same with target flow rate 3000. API gravity, I will just use 38 here, but actually it's a water well. Okay, let me emphasize this is the case of water source well. Okay, so we don't need this API gravity, but yeah, for completeness sake, I will write that. Specific gravity of water 1, and yeah, just to make it brief, specific gravity of oil, it will be calculated from the API gravity. And the water gradient, it's 100% water cut, so water gradient will be 0.433 psi per foot. And wellhead pressure, it's 130 psig. Okay, this is the normal base case wellhead flowing pressure on the field. Okay, so 130. Of course, it will depend on each operation. It will depend on the condition of each field. Okay, but in this case, actually it's a practical case, and let's say the wellhead pressure is 130 psig. Okay, so specific gravity of the mixture. So this is a computation there. We will need the specific gravities from both water and oil, and also the water cut. Okay, because this is a water well with 100% water cut, so of course specific gravity of the mixture will be 1, and the mixture gradient will be there, 1 multiplied by the water gradient, which is 0.433 psi per foot. And flowing bottom hole pressure target, yeah, let's use this one, this calculated. Okay, and pump intake pressure, okay, it will be calculated, and let's check the formula. So the pump intake pressure is the flowing bottom hole pressure minus this one, the distance between this pump setting depth and the middle perforation. But be careful here, be very careful here. It's a hydrostatic calculation, so you cannot use measured depth. You need to use true vertical depth. Okay, you need to use true vertical depth because it's hydrostatic computation. So I need to change this to the true vertical depth version. Later on, I will do that. And of course, multiplied by the mixture gradient. Okay. And oil rate based on this liquid rate and the water cut. Of course, it's 0 because it's no oil. It's only water. Okay, so yeah, I will do the trajectory calculation so that I have fit BHTVD like this. Fit BHTVD. Okay, let me pause for a while. Okay, so the true vertical depths are this one, these two. Okay, so the distance between the mid perf to the ESP pump setting depth is 60 feet in true vertical depth. So the pump intake pressure, I will change it to this. Okay, so the pump intake pressure will be for 182 psig. Okay, so you can see here we have the IPR, the plot here. It's generated using this table. Okay, so it's a very easy IPR. Prepare this table. You have flowing bottom hole pressure there, and then flowing bottom hole pressure divided by static bottom hole pressure, and then the calculated values using Vogel equation. Let's start with the pressure. So here, start with the static bottom hole pressure, which is 800. Okay, and then you can just go down by 90%, 70%, 60%, 50%, down to 0%. Okay, let's prepare the pressure first. And then, of course, this will be calculated just by this divided by static bottom hole pressure. And then don't forget to use dollars there, and then go down to 0. Okay, we will use this column for the flow rate calculation using Vogel equation. Okay, Vogel equation is of course 1 minus 0.2 multiplied by flowing bottom hole pressure divided by the reservoir pressure, which is M5, minus 0.8 multiplied by the square of this, the flowing bottom hole pressure divided by reservoir pressure. Okay, and then everything multiplied by the maximum flow rate. Don't forget to use dollars there. So that's it. You can just drag like this, and then plot using these values. The horizontal axis will be the flow rate, okay, and the vertical axis will be pressure, okay. And this is the, let's say, the target flow rate or the well test data, okay, whatever you want. If you have well test data, you can input here, right, maybe test or target, okay. So it can be test or target. Let's say we don't have well test because it's a new well, so now it's a target flow rate. The target flow rate is 3,000 barrel liquid per day, and the target bottom hole pressure is this. Okay, I get this from the well modeling, which I created on the another software. Okay, so in terms of IPR, it's good. We already have our, our target there. And let's go to the calculation for the ESP itself. Okay, I'm going to squeeze this auto height. Okay, so it's already computed. First is the head in terms of net vertical lift. You can open your textbook, it's already there, and the calculation is this one. So the net vertical dynamic lift will be here, actually in true vertical depth. Okay, be careful there, it's all about vertical depth, true vertical depth, minus this, the pump intake pressure divided by the mixture gradient. Okay, and the head is actually 1,887. Basically, it's the head you need to push or to lift the, the fluid from the pump intake, okay, pump intake depth to the surface. Okay, so that's the head unit. Okay, that's the head you need to provide for the pump. And then friction loss. You also need to provide head to go against the friction loss. Okay, that's what it means. Okay, and friction loss in terms of feet. Okay, if you convert the friction loss to depth or to distance, it will be 65 feet. So how do we calculate that? It's 20 multiplied by this, the measured depth. Okay, because it's, you know, it's friction loss, so it doesn't consider the true vertical depth. What it needs is the measured depth, because it's actually the distance that this is actually the length that the friction is applicable. That's the friction is applied, and then divided by 1000. So it's very easy. And the head for tubing head pressure. Okay, so it's the head that you need to provide to go against the wellhead pressure, because wellhead pressure from the pump point of view, it's actually a back pressure. Okay, it's a resistance. So you need to go against that resistance. If you convert it to length, if you convert it to distance, it's actually 300 feet. How do you calculate that? So here, the flowing wellhead pressure or the tubing head pressure multiplied by 2.31 divided by the specific gravity. Very easy. And then you can just sum them up to get the total dynamic head of 2253. So it's the pump should be strong enough, okay, should be strong enough to lift the water, to lift the fluid to go to this distance. Okay, so that's the concept. You need, the pump should be strong enough, powerful enough to lift the water from the bottom hole to the distance of 2253 feet. Okay, so that's the meaning of the head, dynamic head. And of course, to be able to lift the liquid from the bottom hole, okay, to this distance, you need to have a good pump. And the good pump can be represented in the number of stages that the pump has. Okay, here it's calculated. So what we need to input is actually head per stage. Head per stage will be based on the pump that you use. Okay, so based on pump curve, the unit is horsepower per stage. And don't forget it's TDH, total dynamic head per stage at 50 hertz. Okay, and pump wear, if you have 0%, in this case I use. So in this current picture, it's DN1750N at 60 hertz. So I'm going to change that because the pump that I need to use is actually DN2400. So let me delete it first. And then the pump that I need is actually copy and then paste here. Okay, so this is DN2400. Okay, it's Reda pump DN2400. The optimum operating range is between 1500 to 3200, right? Okay, so this is the best performance range between 1500 to 3200 barrel per day. So the target is 3000. It's still within the good range, still below the maximum allowable, maximum possible rate. Normal housing diameter 4 inches. Okay, still good. We can still install it inside our inner casing diameter. Shaft diameter is this, shaft cross-sectional area is this, and minimum casing size 5.5 inches. So in this case, we have 6.3 inches, the casing inner diameter, so it's still good. And don't forget, it's DN 2400 at 60 hertz. Okay, so if you apply or if you operate your ESP later on in 60 hertz, you can directly use this pump curve. But if you operate it using 650 hertz, you need to do some adjustment. Shaft brake horsepower, standard and high strength, housing burst pressure limit, standard, buttress and welded. Okay, you can read that. Here is the capacity on the horizontal axis, it's the flow rate. And the vertical axis, the left vertical axis is the head. Okay, this is the head we are talking about when we are talking about these heads. Actually, the total dynamic head that we need to provide. And then this is the pump efficiency and the power. So head will be shown by this blue curve, head, and then efficiency by this red black curve, like a dome, and power, the red curve. Operating range is here between 1.5 and 3.2. Okay, so yep. Okay, I need to change it to 60 hertz, and then I assume pump wear of 0%. Okay, for best case, and I need to send it to back. So our target is actually 3000. So here, let's shorten the length there to touch the head curve. Be careful. Okay. All right. And then, okay. All right. So there. So the head starts from 10, 12, 14, 16, 18. So head per stage will be 19. Okay, 19 horsepower per stage. All right. So stage required will be this, the total dynamic head divided by the head per stage. So I'm going to need at least 119 stages, but I can provide more than that, of course. Let's say I can provide 120 or 125. I check on my well flow simulation based on the database that I have. It's maximum at 125 stages. Okay, so yeah, later I will propose that the ESP will be equipped with 125 stages, especially if you also consider the pump wear. Okay, so stage required 119 at least, but I'm going to propose 125. Okay, and then motor horsepower required. Let's be careful here. So talking about the power, there. Okay, the reference will be this right vertical axis. Be careful because I have limited stock for motor. I only have motor 90 horsepower. So I need to be very, very careful here. Let me do some thinning. Okay, to make accurate. So there, yeah, this one, okay lah. So 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. Okay, so 0.7 horsepower per stage. Fingers crossed. All right. Okay, so the pump head per stage multiplied by the total stage multiplied by the specific gravity of the fluid. So it's actually 100, 119 multiplied by 0.7 and then multiplied by 1. So I need motor at least 83 horsepower. All right. So it's close to the border. I only have motor of 90 horsepower. So maybe achieving 3,000 barrel liquid per day a bit too, yeah, not very good, I think, because it's motor, it's electrical. We don't want to play with that. So at least I want to have a good safety factor below 90 horsepower. It's too close. I don't want to have electrical downhole problem. So maybe on normal condition, I will not target 3,000. Okay, let's say 2,500 instead. Okay, wait a minute. So the thing is, you need to change this pump intake pressure and everything will be changed. Let's see, for exercise, pump intake pressure of 500. Okay, 300. It's dangerous. Now you need stronger motor. Yeah, let's see. Let's see, we just go with the flow. So at least I need motor of 83 horsepower. It's quite close to the motor that I have available, 90 horsepower, but I'm going to finish it first. And motor cooling effect, casing ID is 6.37, or let me make it sure. Yeah, it's actually 6.366, the casing internal diameter, whereas the motor OD, okay, based on the motor, it's 4.5. So fluid velocity calculated using this equation. You can read your textbook regarding ESP or regarding ESP design. So you're going to need data from the flow rate that you need, 3,000 multiplied by this constant, multiplied by, or you also need to consider the casing internal diameter and also the motor outer diameter. So the fluid velocity is 1.76 feet per second. So the motor cooling effect still below 0.7. Okay. I mean, it's still greater than 0.7, so it's okay. It's if it is below 0.7, it will be not okay. It means that your motor lacks cooling, which leads to failure. Okay. Your motor is very, very hot during operation, so you need to cool it off. All right. Okay, so we are heading to the final stage. Install pump type. I want to install the N2400 with head per stage here, 19, and bottom hole or brake horsepower, BHP brake horsepower per stage, 0.7. Stage, okay, stage, let's say 125. Okay, as I said, at minimum you need 100 119 stages, but you can actually design to provide it greater than the minimum requirement. So in this case, I put 125 stages, and motor installed based on the availability, it's 90 horsepower. You see motor installed not okay. So gas handler, head per stage, stage 1 stage, brake horsepower, 2 horsepower, okay. And total head ESP installed is 19 multiplied by 125 stages. Minimum requirement is actually for the motor. The stages 125 multiplied by C55, this, okay, and multiplied by C27. Specific gravity is very important, and then plus the gas handler C61 multiplied by this, the brake horsepower needed by the gas handler, again multiplied by the specific gravity mixture. So at the end, you need 107 horsepower. It means that your motor is too small for that operation. Okay, so pump sizing okay, but motor installed not okay. So what do I need to do? I need to lower down my flow rate target, okay, which lead to changes in pump intake pressure, okay, or leads to change in flowing bottom hole pressure. All right, so I can make flowing bottom hole target based on back calculation of the flow rate. Let me think for a while. Okay, so let's say I want to operate at 2500. Okay, so I'm going to have, let's say, between, I will, yeah, it's the trick that you can use, or maybe this is test or target. I will use another here. Okay, 500, let's say. So it's this divided by 800. So the flow rate will be this. Okay, this is just for trial. It's a trial run to estimate the flow rate that I need to target below 3000 to make the motor usable. Okay, 90 horsepower. So I'm going to need this what if analysis. So what is the bottom hole horsepower? What is the flowing bottom hole pressure if my target is only this, only 2500? Okay, what is the flowing bottom hole pressure? Okay, so 566 bottom hole pressure leads to flow rate of 2500. So if I change it to this, so the pump intake pressure is 540, lower down my dynamic head. So I know I only need minimum 112 stages. So instead of 125, I can install 120. Motor installed still not okay. Yeah, motor installed still not okay. It's very heavy operation. Okay. I already reduced the dynamic head and thus reduce the stage required, and thus I also need to adjust this actually to 2500. Okay, good, 2500, still in optimum operation, or I preserve that. Sorry. I put it here. I copy another line. I color it green instead. Okay, but it's at 2500, and there you go. Okay, so the head first. So the head, it's 10, 12, 14, 16, 18, 20, 22, 24, 25. Okay. Oh, okay. And then, so change this. What is it? It's 0.65. Okay. It's 0.65. Okay, so far so good. So stage required 85, and then motor required for the pump 55. So now it's much less. The number of the stage required 85. So 25 there, 0.65 there. So actually I can provide, let's say, 100 stages instead. Motor installed horsepower 90, motor installed. Now motor installed okay, because minimum required it's only 80 horsepower and the available motor is 90 horsepower. So motor installed okay, pump sizing okay. If now I lower down my target flow rate to 2500. So design ESP, I change it to original target ESP. Okay, and add possible operation, possible target. Series X is 2500. Oh no. And Y here. Okay, so or I delete it first. original is, oh no, original target is 508. Original target is 3000, so I'm going to goal seek to 3000. Yeah, so the original target is 3000 liquid per day, 508 bottom pouring pressure. But now the possible operation with the available motor that I have is 2500 and 566. So there, I'm going to format data series, marker, let's use triangle, and then color it green, border also green. Okay, and then format data series. Change format data series. Sorry, format data labels. I mean, it's not that. Series name. It's possible what? Sorry. Okay, so possible, or maybe ESP. Sorry, ESP motor 90 horsepower, because this is the motor that you have. So ESP motor 90 horsepower, and this is the original target. Okay, so if you have everything good, big big motor, available pump, you can target 3000. But considering that you only have motor of 90 horsepower, you need to lower down your target. In this case, I lower down my target from 3000 to 2500 so that I can go with the execution, but with the restriction that I have, which is restriction in motor availability. I only have motor of 90 horsepower. So I lower down my target to, you know, to 2500 barrel liquid per day for my water source. Okay, so again, motor installed okay, pump sizing okay. So there you go, the practical case of ESP design using spreadsheet, using practical data, practical information, and the real ESP pump curve. That's all. I hope you enjoyed this video. I hope this video is useful. Thank you so much for watching, and see you again in the next ESP artificial lift or Eng-Man videos. Thank you.